That's awesome.
This is
You don't have to worry about
this is
it.
science fiction.
I know.
Oh my God.
Hey Dave, if you have time, swing by and say hi to the team for me, including NIC. So text me back if you have time. If not, then I won't introduce you.
Yeah, I'm not sure.
Hey,
I'm not sure, but I will let you know as soon as I know. I'm definitely going to be able to go to Da Nang.
Okay.
Okay. So Tian, I just put a poll because there are 66 assigned and we have 59. So I wanted to have a poll. So Dave and Wu, it looks like there are 5 people cannot open the assessment. Okay. So there are 7 of people. You say lý do khác.
Are you sharing, Phil, or no?
Oh, okay. So, let me share this here.
No, I see it. I think you share.
Oh, am I sharing?
Yes.
Does anyone else see it?
I don't see
or
it.
Should I share the screen? Let me just share the screen.
I don't see it in Phil. I only see the
Okay, so this is I don't know where is it. I can't make it bigger. But can you read? So the poll is that
I just see your laptop, Phil.
Laptop.
I mean the laptop display, the screen only. I don't see.
I do see the poll that pop up right on title poll 6. I do see it, the poll, but the screen is not sharing. That's all.
Let me share the screen again. So I'm sharing. Let's share the screen number 3. Okay. Do you see the poll on top of the?
Yeah, see your screen now.
I see the lecture 4, but that's it.
But it's not on top of the screen. That's weird.
And Phil, can you share the poll? Share the screen?
Yeah, let me see if I can do that. Share. I don't see the poll on top of the share. Let me
just ask the student to see if they can see the poll.
Yeah.
Poll popped up automatically for me.
It does.
Yeah, and our 5 minutes. Our 5 minute break is over, so the students are waiting on us.
Yeah, does anyone who can share the poll? I don't know how to share it though. Maybe I just do a screen dump.
I think we have to end the poll to share the results.
Oh, maybe that's what it is. Sorry, share result. Okay, my inferior. Do you see it now?
Yes, we can see it.
Okay. So does it, Tian, you see it?
No, I don't.
Anyway, okay, why don't we just, so I just read in, there are like 6 people cannot open, and there are 8 people, there's some other reasons. 2 people say no time, 3 people say no knowledge, and 2 people say they don't know if they have to do it. So cho mọi người trong cái poll này có 2 người không biết là cần phải làm, thì bây giờ cũng biết cần phải làm, tại vì cái poll mình cần làm trước khi mình học để mà cho mọi người biết là coi như là cái kiến thức đến đâu, để mà mình có thể dạy cho nó được. Còn mà có những người mà không có mở được thì xin vui lòng liên lạc với lại TS dash có một cái địa chỉ có thể Vũ với lại hoặc là we can share the địa chỉ, xin vui lòng gửi cái chi tiết về cho Vũ với lại Dave để mà hai người đó có thể giải quyết được. Ok, Thiện, go ahead, Thiện.
Ok. Ok, xin chào mọi người. Thì hôm nay mình sẽ làm cái phần 2 của cái lab 2, tức là mình tiếp tục làm cái phần import. Thì cái lecture là anh Phil đã nói rồi, thì bây giờ mình sẽ load một cái design rồi mình thao tác trên một vài cái dữ liệu mình có. So let me share my screen here. You guys see my screen yet?
Yeah, yes, Dan. Let me see your screen.
Okay. So so the format of the lab is very similar. So with the part 1. So this is part 2, right? So so the first one here is just I want to show you where how's the data is get structured, right? So we have lab 2 import, and underneath we have the database access, lab that optionally you should do. And then last week we did part 1, and today we're gonna do part 2, right? Like break these important file that we're gonna see.
This meeting is being recorded.
And then the IO placement. So I think Phil already showed that, but we're gonna dig a little bit deeper, open the file up and take a look at it. Here it's very similar to part 1. So we have the lab, the layout exchange format file. And then we have the timing library, right? And then the lib, the timing is that the timing. So we need 2, right? So we need the physical aspect, and then we need timing aspect. So we pull in, and then we take it in the design. And I put together this, import article. So we're gonna look at it as well, to make it really simple. Similarly, the data is in here. I put it under lab 2. So if you did part 1, you want to do it again, to copy the part 2 over, so we can do the lab here. So I just want to look at the important article, right? So I show it here. I will, if you look over here, so under part 2, we have import, right? So if I open this up, so it's actually it's pretty simple, right? All we have here is the top here we say, okay, so we have a power net, called VDD, and then we have a round net called VSS, right? And then the next one, this is even though it's just one line, but this is extremely important, right? Because all of the information that describe your environment your design, your timing is in here, right? That's the MMC, right? We're gonna take a look at that later. So this one gonna contain all of those timing information in it. And then the next section is, we read in the physical aspect of it. So in this case, we have all the list of the lab file, right? And I think last week we did look at this one. So the top one is extremely important, right? That one has the technology definition in it, right? And then all of these are essentially, you can tell by the name, right? These are for the path, right, or the I/O, and then we have all the memory, and they located in here. So if you want, you can go here, take a look at them again, right? So the first, we do the read MMC. That's the timing information. And the second one is we read in the physical data, what is contained within the lab file. And then the third one is the connectivity, right, of the design. And that is the netlist, right? So, and this one is just saying that, yes, you can read in multiple netlists, but then you have to decide, you have to tell the tool which design you want to, make a top design. In this case, we have only gone top design, but it was its ASIC entity, right? So after you do all those three things, right? The timing, the layout information, and the connectivity, then you say design, right? Read all of these in, combine them together, right? And when you've done that, your design is in the memory, right? And for this case, we say, well, but I want to do something extra, right? So we're gonna create all the I/O ring in this ASIC entity, and then we create a floor plan. So it's just easier for us to look at. So if you look what's back in here, I already did all those for you to save you time. So here, right? So you can see here, I invoke the Innovus, and then I source the import, right? The one that we just look at, the import file. And then, so after this, how you source this, and this is what we have here, right? And in this case, right, we can switch between the layout and the physical view, different view that we touched on I think the first week, right? So this one, let me zoom out here a bit. Yeah, so I think Phil did mention about this one, is that this essentially this is what they call a target utilization, right? It's currently calculated as 84%, right? So so initially you want to look at that number. If it's too high, then you more likely you want to increase the die size, right? If the number too low, it could be path limited, then not much you can do. But if it's not path limited, then your design is constrained by the path ring, right? That not the case, and then you can decrease, make the dice a little bit smaller, right? To it depends, but usually between 70 and then 80%, right? So it's reasonable. So let's go back here. I think we covered that one, the import. And so we did after we look at it, we actually imported. So let's see what I have here. So in the GUI, change the floor plan view. Oh, okay. So you want to verify the path order and then compare with the IO file, right? So let's do a mini exercise. So what I'm saying is with this, floor plan view here, see, let's say zoom in, right? So because we just read that import, and then magically all these IO get placed evenly, right? So if you notice, the space between these pads, you can measure them, roughly, they are exactly the same, right? Because that's the default behavior. It's gonna, all the pad on the top will be placed evenly, right? And then on the left side here, it's gonna be different because the number of pads are different from the top to the left side, right? So let's see. But let's look at, let's come back here. So let's look at this, IO. So where is it? So it's under data, right? So if I open the data here, so we have this here, ASIC entity IO, right? So, okay. So let's see here. So we have global. So that's the syntax, right? You say, let's see the IO pad portion, and I'm looking at the top section, right? So let's see here. So we have MDC. Okay, so that's the first one, MDC, right? Zoom in a little bit more. And then TXD, right? So it start from the top left, and then it's go to the right. So we can just do double check at the end here. Let's see. Yeah, something with the Q underscore N, right? So if I go here, so that's my top portion. I go down to the end, right here, right? So QN. So we verify the top, right? So I'm not gonna do all of it, but I leave that to you. You can do the next or verify all of them. Another thing is when we do a real chip, really, we're not gonna use this. We're not gonna do actually all the pad gonna be evenly spaced, right? That's not realistic, right? So we actually go in and actually determine where we want to place the pad, right? So right, but so this exercise is good. Yeah, it just look at how many pad and then it just space them out, right? So okay, modify the pad order. Okay, so let me see. Yeah, I think I can do that quickly. So let's do something fun. So let's see here. So I'm gonna go to the top again. So right now we have MDC, the top one. So I'm gonna just move it to the second, right? So I say right there. Okay, just want to verify. So right now, MDC is still the pad number 1, right? And the TXD underscore 0 is the second one. So I just update the ASIC entity.io. Nothing happened yet. So I have to switch back to the Innovus command here. And then I'm going to say read IO file. and then we say data basic entity.io, right? So let's try that. And let me refresh it. So just as we expected, the order of the path has changed, right? Because we update the text file, we reload the text file. So that's one way you can do, you know, you can make change and you run it over and over until you're happy, right? So we done with number 3. Okay, any questions so far? Let's see here. Okay.
Quý vị học viên nên nhớ là mình đang học hỏi nha, học phải có hỏi nha.
Yeah. Nếu mà dễ quá thì không cần hỏi. Okay, so we're gonna do the next one, number 4 here. So this is very important as well. So we're gonna look at the view definition, right, or the MMC file. So let me switch back to here. So this is under data, right? Part 2 data, view definition. So okay. So I feel already cover the lecture, but I just want to touch on a few things here. It's kind of like go backward, right? So this file is more like you do bottom up. You define the lowest structure and then you build on top of it, right? So for me, usually I go and I do it in reverse, right? So if we go to the bottom of the file, and we say, wow, so essentially this is as the highest level, right? Is the analysis view, right? So you think of the analysis view is like you have a chip, you want a chip to operate at different you know, you put the chip in different mode and timing, right? So if you look at this one here, let me see. Okay, so the analysis view, it has essentially two big item, right? So the first one is the delay corner, right? So essentially say, wow, how's the timing look like, right? And then what is the mode or the constraint for that, right? So it have two, you know, element, right? Timing, fast or slow, and how it's operate, right? Is that functional or is that scan mode or some special mode, right? So one is the behavior and one is the timing, right? So that's the highest level, right? And then you kind of like, okay, so how you define the delay corner? You go back here, say, oh, create delay corner. So the delay corner have two portion, right? So you have the cell delay, and then you have the RC delay, right? So that's what it's combined here. So you have timing condition, which up here essentially it's just a library set, right? It's just a combination of different library set for a certain corner that you want. In this case, it's like you want to define a corner that all the cell is very slow, right? So that's for the cell. And then the RC is for the interconnect, right? So you have two, again, the delay corner have two pieces of information, right? The cell and the interconnect, right? So and right here, let's say how you do the RC corner, right? You have all of these, you know, technology, you know, and you can scale up, scale down right here, right? So, and then for the cell delay, you have to create a library set, right? So you look at the chip design, you have different library, characterized at different, corner. And then you group them together. Say, well, realistically, if I'm in a certain, operating condition, I want to simulate that. So you pull in all these library cell and you create that condition, right? You want to simulate that. So and then that's the you have the timing, and then you have the behavior, right? This is where the constraint mode come in, right? That's where you have right here. So how the chip gonna behave at certain condition, right? So so I said here, so we have the create analysis view. That's the highest, and then that one need the delay corner and the constraint mode, right? And then the delay corner, you have the RC corner and the library set. So yeah, you take a look at it, essentially get familiar with it. I think, do we have that? Okay, so we do have that. Okay, so let's move on to the next one. Okay, I want to do just one example here is that we have two timing library set in this case. I think we have the create timing set. Create a library set. So the first one here we call is fast, right? So it's like we're gonna go in order fast library, right? So fast mean that we have minimal delay, right? So in this, timing simulation, the cell is very fast, right? So and I want to look at, we're gonna pull up here the fast.left, and then similarly, we have I think it should be another one here. So this one is slow, right? So we have the slow library. So let pull. I already have it here, but I want to do it live so you can see. So library, we have the left. We look at that. And let me close that. So you can see here under the library, we have the max and min, right? So essentially max means slow, min means fast, right? So this is where I expect the slow to be in here, right? Slow going to be under max here. So let me open that up. And then for the min, so I'm going to do the fast here, right? So I'm going to do, which one I do on the top? Okay. So I'm going to do the fast on the bottom, just like what we have here, right? So in this exercise, I want to, because it's just so many cells, right? We want to look at the D flip-flop here, just randomly, just pick one. So we have the D flip-flop HQX1. X1. Okay, right there. So let me move on top. So I'm going to do the same here. Okay. So if you look carefully, it's the same cell, right? And because the fast, and say, oh, so what's the difference between fast and slow? So I think in the lecture, Phil already mentioned that, you know, essentially we look at, so within the library cell, it has many pin, right? So we have, because it's a flop, so we have the CK pin. And you have all these, you know, information, the input direction, capacitance, but we want to look at the Q pin, right? So we have D pin. It's all the same, but you know, I think it's more interesting. We look at the output, right? So we have the Q pin here. Okay, so top here, I'm gonna look for pin Q. Okay. So I think this is what I have here as well. So you can see the Q pin is a flop. So yes, direction is output. Max capacitance. Yeah, later on, you know, at the end, you know, we have some DSC check, right? So that's where the max capacitance gonna come in. So, and then so the timing. So for this Q pin, they have the timing information, right? They call timing here, and they call related pin. So the way you think of this is CK, the Q pin is related or clocked by the CK, right? That's the timing art, right? And I think Phil already mentioned, so this is the timing table, right? You have the index one, which is the input sleeve, and then the index two is the output load, right? Output, right? So it's like a lookup table. So you have index one go this way, and then index two go that way. So if you look at a cell, you have two number, right? The input sleeve and the output, output load, and then you can say, oh, where is it in this table, right? So so you look at the index one here, index two here, they're identical, right? That's how they characterize. And because this is slow, so the different here, let me look at the first one here. The first one here is 266, or almost like 266 picosecond, right? For the same slew and load. For the fast one, it's only 92, right? So essentially it's about 3 times faster, right? So, and this one, the last one is about 0.8. Let's say 1.9. So it's a little bit more than 2x, right? So it's not going to be linear. So, but that's why you see that's why this is fast and it is slow, right? So, and just so many cells in here. I just hold on, is that cell? Okay, so let me do this. Right, so you can see just so many, right? So yeah, it's like 500 different cells in this library. So we just do like one, right? So you can do more. I mean, the lab is just want to give you get you to start in this journey, and then you can study a lot more. You don't limit by what I put in the lab here. So okay, so that's number 5. Okay, so we have the timing library tell you how fast, how slow certain cell gonna be, right? But then when you design your chip, you have to come up with how fast you want to design your chip, right? So So you go out and say, well, my chip gonna run at 1 gigahertz, right? Right. Another company gonna say, okay, but my chip run at 2 gigahertz, right? So where's that come from? So when they design that chip, they have the constraint, right? The target performance, right? So that's the next one we're gonna look at here is the timing constraint. So let's go back here. I think I have to reset my. Okay. Timing constraint. So look at. So we done with this. So go back with the data. So let's look at the view again. Let's see, look at this one. So just review it a little bit. Okay. So in the MMMC, we define this create constraint mode, right? And we name it, say, oh, this is a functional. That's the behavior, right? We want to create this functional. And in this case, it's a slow functional, right? And we associate the two things, right? We associate the SCC file, we call it here, right? Slow max top constraint, right? So we're gonna look at that. So slow max top constraint. Slow max top constraint. This one. Okay, so let's look at that. See here. So this is the constraint, right? Top level prime time constraint. Okay. So the most important thing is the clock, right? So because our design is synchronous, right? That means everything is to be clocked by some clock, right? So the first thing you come in here is you can define all the clock in your design, right? So you have like create clock, you have a name of the clock and the period, right? So the two things, the period and then the waveform, right? So in this case, I think it's 50-50, right? The duty cycle. So let's say 40, you have 0 to 20, right? So it rise at 0 and it's fall at half of the cycle, right? So it's 50-50 duty cycle. It doesn't have to be that way, but I think some of the simple design is going to be like that, right? So 32, 0, 16, right? And actually all of them the same. So by looking at the period, you know which one is fast, which one is slow, right? The one with the higher period or longer duration, that means it's slow, right? So in this case, this one is the fastest clock here, the period 4, right? So these are very important, right? So more likely, the one that fast going to constrain your design more, right, than the one that runs slow, right? So you have more time to do something, right? So, and then, so that's the clock. This clock has the latency, right? Latency is just quick, a simple way is just say, well, it's a delay, right? So, yeah, when you learn about the clock tree later on, then you understand the latency more. It just, when we don't have the clock tree, it's just the latency, right? So, and here, yeah, we have the set input delay and then set output delay. So I think one way to look at this one is if you have a chip here. Let's see. Let's go back here. So I believe this is the input pin or input pad, right? So input delay is the constraint, right? So this input gonna come into the design and say, so you need to tell the design when I expect the signal gonna come respect to the clock edge, right? So that's where the set input delay come in is that, yeah. So it's say here, set input delay respect to a certain clock, right? So when that clock rise, I expect my signal to be no later than 4.5 nanosecond or whatever picosecond, whatever the unit is, respect to, you know, for that port, right? So, and then same thing for output. Right, so output, so you need to constrain this. So it's interface with something else outside, right? So that receiver end have to know when your signal gonna come, right? So say, wow, my signal not gonna come, you know, later than 1.5 after the clock, right? Something like that. So
Hey, Tian, can I interrupt? There's a
yeah,
question in the chat room asking 4.500. The unit here is nanosecond or not?
I believe it's nanosecond. Yes.
Okay. So I hope that answers your question, Lê Quốc Huy. Yeah. Yeah, go ahead, Tian. Sorry.
Okay, sorry about that. My kid bothering me a little bit. Okay, so yeah, I think that's the old nanosecond. So you can see here, yeah, I mean, the clock period is very long. So relatively, you know, it's like if you have like 40 nanosecond, so you lose that like 5, you know, 5 or 4.5 nanosecond for the input to come. And then you have the rest, right? You have like 30 something for your data pad. Okay, so let's come back here, make sure I'm not. Okay, fast clock. Okay. So by looking at the constraint, you know how the clock defined, right? But once you already have the design, you don't want to go and look at the constraint. You can extract that information from the Innovus, right? So let's try that. We can do that here. Say, okay, I already have the design. I can see how the clock, you know, define. So you do a report clock. So this should contain exactly the same information that we just looked at, right? So let's see here. Okay, so we have all the clock here, and you see the period. So we look at some of them have 40, right? The fast one is in my, you know, clock 2x here is 4, right? And they tell you like, remember that 0, the 50% duty cycle, the leading edge and the trailing edge, right? So that's where it's rise and then that's where it's fall, right? And all of these are non-generated clock. That means it's a clock defined at the port or pin. It's not, you know, generated by something else for another clock, right? So if that's the case, then we have what I call a master clock and then the generated clock. So real design, we're gonna have many of those generated clock, right? You have a one master and then you have multiple generated clock later on. Okay. So I think that the main, the key here is, I think, the timing report here. So, you know, how do you know your design is, you know, meeting the requirement, right? You know, timing wise, you do report timing, right? So report timing. the first time it's going to take a little bit of time to run. Okay. It's it's very hard to look here. So let me. And you don't have to do this. You know, if you have, you know, you can write into a file and then you pull up in a text editor. It's just easier. You know. I'll just call it. You know. I just redirect into Pad 1, so I can pull up in my editor here. It's just a lot easier. So example 2. So I have this Pad 1 here. I can pull it here. For me, a lot easier. Okay. So I think I was asking whether the design is meeting timing or not. Obviously not, right? We have violated here, right? So we not meeting timing. I mean, we need to do some work here. But unfortunately, you know, fortunately, this is not the end. We just add the import. So so that's the view. So if you look at the view, let's see here. I just want to see how things kind of like all things like connect together, right? So it's, you look at the report and say, what's this view come from, right? Remember the view definition file? So if I go here, I look at the func max. Right here, create analysis view, name func max, right? So this timing pad we're looking at here is for this func max view, right? So in your design, you can have multiple, you know, even hundreds of view, right? In this case, the timing violation is for this view only, right? If we're gonna do for this another view, I think that's a name, and I think we have only one view. Let's see. Okay, we're gonna try to do another view here. The timing gonna be different, right? So, so this is func slow max. So we're gonna do func fast min. So let's do another one. You can do view. Okay, so that's another thing. I think you have to. Man, let me source it. I think it's had to be early. Let me try that. But I want to show you is that in this analysis we have two view, right? One fast and one slow, right? So so in this way, in the Pad 1 here we have is the slow one. We have that's my clock. And the clock, so my clock. So if you look at the constraint and you look at my clock, right here, create clock, my clock. The period is 8, right? So clock is 8. So that's how you can, you know, sometimes you read the timing constraint and you have to go back. Timing report. I'm sorry. You look at the timing report. You have to come back to the constraint. You verify, right? Is that the intent? Is that clock defined correctly, right? So you just don't assume whatever you see in the timing report is correct. You have to verify, right? So that's it. So what it does is calculate, when the data arrive, and then say calculate the expected the arrival time, and then it's compare, right? If it's late, it's later than the expected time, then you violate or you fail, right? If you come before, then you meet timing, right? So okay. Make sure I cover everything that I have it in here first. Report timing. Okay, that's what work below that. So is the design meeting timing? No. What is the clock and its period? We did that. Is the report max or mean timing? We answer that, right? So this pad 1 is max. What did it do? The pad 2. So you better look at pad 2 here. Oh. So I have pad 1, pad 2. So it may pull up pad 2. It's going to be slightly different, right? So pad 2, see the view, because I purposely did for a different view, right? You can see the pad 1 here, but yeah, the name is different because I do 1, so I only went pad 1. But the view is Fung Slow Mac, right? This one, the pad 2 report here is Fung Fast Min, right? And this one is the IO, the default, right? So yeah, it just go from a clock to a pad. So what else I want to look at? Timing iPad. Okay, I think Phil already mentioned this. What's the WNS, TNS, and FPE? So this is the worst negative slack, right? That means like the worst slack in the design, and this is the total negative slack, right? If you look at all the pad that has the negative slack, you sum them up, right? That's what you have. So, and this is how many of them, right? Failing, right? So failing endpoint, right? So, so let's see what else I wanna. So I think Phil, you did mention about the summary, right? So let's see. So let's say you want to do more than just timing report. And then you can do, let's say, do report. The thing is, you don't have to remember, right? You can just do help on.
Maybe report timing summary or something like that. Right there, the last one.
Right. That's a lot, right? So we have report timing. These are a little bit more advanced, right? But for today, we can do this. Okay, so because the last timing report was in early mode, that's why I only do you only see the whole time, right? So, and that's what the worst negative slack is. They break it down, right, into different type of timing. So we have the asynchronous, we have the in to out. Essentially, it's just from the input directly to the output, right? And then we have a rest to out, which is the flop clocking an output, right? And then the next one is into rest, which is the input coming in and captured by a flop. And the last one is from a flop captured by another flop, right? So it's breakdown. And so right now, it's rest to out is the worst, right? So, but because we very early, we don't have a real clock yet, maybe the constraint is not correct, right? The latency maybe is skewed, right? Not correct. So early on, probably you want to look at this, rest to rest, because that independent of the clock latency, right? So so that's the worst, and then the total, and then how many, right? So even though the rest to out is look very, very bad, but only 5 of them failing, right? But then rest to rest, even though it's only minus 413 picosecond, but look how many of them failing, right? So you have to look at 2 different things, right? You look at the worst and how many of them failing, right? So and the sum of that is this number, right? So you look at all of that, and then so here I was saying that delay. So they actually, the good thing is they even tell you, right? So say, well, I want to look at the setup too. I don't want to just look at the whole, right? So by default, the tool only do setup or whole, right? To save the memory footprint. But sometimes you say, no, I want both. I want setup and whole at the same time. So you do that. Let's see, what is it? So even the constraint is not up to date. So whatever the document they have here is not up to date. That's the legacy. So instead of set global, with the common UI, you have to do the set DB, right? So remember that, set DB. And now I do the same thing. Report timing summary. And then I expect to see both whole and setup. So it's rerunning timing right now, right? So, okay. So it's came back. So yeah, as expected, we have setup here. And then we have whole here, right? So because we forced the tool to say, I want to do both, right? Calculate both timing, setup and whole for me, right? So yeah, so we have some DIV here. Yeah, DIV, derived, yeah, we can look at that later. Essentially, it's failing MAC transition, right? Okay. Let's see what else we have. Okay. But sometimes you say, well, I don't want to just do the command. I want to see it, right? Say, wow, there's a way you can see it too. So in here, you want to look at the report graphically, right? So you go here, you do that. That's the timing menu. You do the debug timing. You go here, and so if you have the report, you can load the report, or you can generate a report, right? So for now, it just generated. So it's run, as you notice here, it's run the report timing. By default, it's going to run 10,000, and that's the report, right? All right. So, and then the nice thing is it's going to load up into this GUI You just see. So this is the histogram, right? So the red one are the violation, right? So you look at between the red and the green, that's 0, right? So on the right, those are the pad that meeting timing, and the red one on the left up the 0 are the one that not meeting timing or failing timing, right? So by looking at this, say, wow, there's quite a few failing here, right? And then on the bottom here, they're gonna list by the slack, right? So the worst one on top, right? You keep going down, right? Just so many of them. Though it's only up to 50, right? So and the nice thing about this is you can actually zoom in here, right? So you can actually say, okay, I want to look at, if you zoom in here, say, oh, what are these one, right? So you double click on it. Oh, only one, right? One. So this is the worst one, and you can double click on that one. It's to tell you the full path, right? So tell you to see the time that launching, and that's the data path delay. So there's many tab here. You can have the data path, launch clocks, right? So to tell you capture clock, and even tell you, where's the constraint come from, right? It's actually tell you exactly where all the constraint come from. Is that awesome? Right. So to tell you that's how are the clock defined, right? All these clock uncertainty, right? So, and then you can, nice thing is you can look at schematic as well. Wow, look at this pad. So zoom in here. So this pad is, so this is the launch portion of it, right? So I believe this is the clock. Okay, so this is the pad, and then that's the clock coming in, and that's the flop, right? So your pad start from here, clock to Q, right? So this is the Q pin. As soon as you clock it, that's your Q pin. It's go to so many, right, states of logic, right? Just like that. And then it get captured, right? Look at this, so crazy. It's get captured by another flop, right? So this is the clock that capture it, and that's the data. Let's go to the, I believe that should be the D pin. Right. Right. When you click on this, it tell you right there, DFFD, right? So, and this one should be the CK. Right, CK pin, right? So let me zoom out. So your pad, the data pad, extremely long. You come in here, you clock it. So the one way to look at it is you have one cycle from this flop and to this flop, right? So as long as you have the delay, you sum up all these the delay here, and then if it's less than one cycle, then you meet timing. If it takes longer than one cycle, then you fail timing, right? So so that's the worst one. Say, well, let's look at some pad that actually meet timing. Say, okay, you can zoom in here. Double click on that one. So we with this bucket, we have 3, right? So I say, okay, let's look at this. Pad here. So this is the data pad, right? It's launching from a flop. All right. CK2Q here, that's the art, right? And it tell you what the cell is, what's the delay, right? The sum is just add up, right? One state after another, right? The first state, of course, is the same. So you hear the second state, it add the first one to the second one. You get that, right? So let's see, it's pretty long, and it's captured by another flop, right? And you can see here, right? So I think when I click here, it doesn't relate on that. Okay, right here, right? So by just looking this, so this is the delay. So it's very even. You don't have something that stand out, right? Most of the delay is about the same, about 100 picosecond, right? So the first one, probably the biggest one here is your first flop, right? It's about 400 something picosecond. So this thing is really nice because you can quickly just scan this and say, wow, is there something wrong, right? If you see a big delay here, and maybe that cell is overloaded, right? It's just too small, have too much load, right? So by looking at this, that's fine, right? The timing look good. No wonder it's me timing, right? So look at schematic as well. Yeah, this one, right? It's very evenly. It's not too crazy as the first one. Okay, so I think I'm almost done. Let me see what else I want to show you. Let's look at a few more here. Oh, this has the memory. Let's look at that. So you come in here, go through the memory, and then go out, right? So it's the same thing. So it's, I think this is launching. So we can data pad. Right. So because go through the memory, you can see the big chunk right here. I believe it should be the memory, right? So yes. Let me see here. Make it long. So right. So the first one, you see the delay bar here. So about 80% of the delay due to this memory, right? And that's expected. The memory take a lot of time from read to write, right? So this case is, I think it's a read, right? You read the data out of the memory. Of course, it's going to take some time, but right here, the delay bar is break everything down for you. It's pretty easy to look at. So the timing, just to get the timing out from the memory, it takes 2.2 nanosecond, right? Compared to everything else is 100 something, right? So, but the sleeve look okay, right? So this GUI is pretty easy, it's kind of, if you know how to use it, it's a quick way to debug timing problem, right? So it's pretty useful. It's gonna take a lot of time to get used to it, but it's there. And this way is essentially a histogram, right? It tell you how many failing, what's the worst one. Okay, so I'm gonna stop right here. I think that's all I have. And then I wanna hear from you. What's other question? Is there any question, Phil?
Yeah, I tried to answer them with text, but I can read different questions, and then we can cover more if needed. So so basically, TA Khánh Dương asked, why do we need MMMC, right? Why do we need it in general, and why we need it in Blazing Rock specifically? What is multi MM and what is MC? How many modes are there in build design, and what we need to take care of them, like scan and MBIS? What do we need to do?
Right. So I think you think of when you design a chip, right? You have a target performance, right? And you have a target say environment, right? Let's say if I design a chip for a car, right? So my requirement gonna be different, right? So I expect that chip to be inside the car, near the engine, right? So I'm saying, wow. So I need to simulate that chip at, let's say, 125 or even 135C, right? And then if you design a different chip for like indoor, or you even sell to some northern country, they never get 135C. So it's like, no, I don't want to over design my chip for that environment, right? I don't need to simulate that corner of 135. 125 is good enough, right? So, and then the same thing, right? For a car that's going to be minus 40C, is that realistic, right? So if you use say an IO T chip, inside a market, right? Then maybe you don't need it, right? Because it's more likely it's gonna be room temperature, right? And then you give it some margin. So the idea is that when you design your chip, your target, target use for that one, right? How the customer going to use it, right? So that's why a multi-corner, right? And then within the same chip, right? Let's say functional, I expect people to do certain thing during functional, right? But let's say scan mode, the customer not going to scan my chip. Scan is purely for testing, right? So I have a different requirement during testing, right? So I don't need my test, my scan when I'm put the chip in scan mode. I don't need to run like super fast, right? It's not needed. It's purely for testing, right? So that's why we have multi-mode, multi-corner. It's that you simulate the target environment that you want your chip to operate at, right? So if I'm in functional, I'm gonna simulate, right? Extremely hot, extremely slow, and then extremely cold, extremely fast. So hopefully, with those two extreme conditions, I'm gonna be covered, right? But now with the new technology, you have to do more than that, right? Because you have to switch. Sometimes you have the fast, and then later on you're going to learn about different VT, right? So they behave very different now. It's not like the old technology. So that's why in the new chip we have cross corner. We have like hundreds of view to simulate all those, different, environment, right? So the bottom line is you have to think how the chip going to operate, and then you try to simulate that, right? So because if you miss that, and then people are going to use in that unexpected environment, your chip going to fail, right? Because if your chip is not designed for minus 40C, then you take that chip, you put in a car, you drive to like the North Pole, it's not going to work because it's not designed for that.
Yeah, so I think people understand multi-mode I guess, better than multi-corner based on what I saw the questions asking back and forth. So I want to add to what Tim was saying, right? Scan mode and functional mode. For example, you have a chip that operates at 300 megahertz. In functional mode, you're doing DSP, etc. But in scan mode, you're testing your circuitry and you're running it at 10 megahertz only. So you would have two modes, scan mode where you feed in the clock at 10 megahertz, and functional mode, you feed in the clocks at the system clock at 300 megahertz, and you do your timing analysis, and you're fixing them one mode at a time. Versus multi-mode, you define those two and you say, you tell the tool, you aware of these two, you do concurrent. The key is concurrent, right? Concurrent analysis, concurrent fixing. So you don't have to worry about, fixing a timing problem in one mode that will mess up the timing problems in the other mode because they set the circuitry. So in the old days, we do one at a time. And then, 10 years, 20 years ago, multi-corner, the tool become more sophisticated. They can do concurrent analysis and fixing. So that's good. So, the latest question relate to why do we care about multi-corner, right? So we do care because multi-corner relate to process variation. As you know, it's not a single point that you're looking at. There are variations from one spot of the chip to the other in terms of delays, right? That relate to process variation, manufacturing, as well as operating temperature and operating voltages. There's so many different things. So you want to model all these extreme cases, and they're mixing. Like for example, you have a case of fast N, slow P transistor, all sort of complication. And if you don't define everything together and do concurrently, it's a nightmare to sign off timing for all different combinations. So that's why you need multi-corner, just defining everything and let the tool deal with the complexity.
Okay, thank you. I think there's another question about the I/O placement. I think I did mention about it. Look at it again here. So I think the question from Ngô Thái and Hào, right? I hope I say it right. So let's look at what we have here. So I think he's asking about if we have too many I/O. So let's say in this case, because this one is just a simple chip, right? So let's say we just look at this. So as of this point, the tool is expect with the logic that we have, the chip gonna be with the allocated side that we have, the chip gonna be at 84%, right? So okay, so what it means is that this, when I place older cell, in theory, it's gonna come back with 84% utilization. That's a little bit high, but I think it's doable, right? And then you look at the pad, say, okay, so we do have space here. So it's not, in this case, it's not pad limited, but because of the utilization is at 84%, so more likely you cannot make the chip any smaller, right? Because if you make a chip smaller, to say, well, because you have space here, you can squeeze the chip smaller. No, because if you make a chip smaller, what happened? This is not going to be 84% anymore. It's going to be 90%. And that's just not realistic. You're not going to be able to route a chip, right? So in this case, so what if you have, what you have here is only 20%? That means we don't have a lot of logic, right? A lot of empty space here. And then we say, oh, if that's the case, then we can, eliminate all these spacing between the pad, right? And then you're going to make the chip smaller to a point that there's no spacing between the pad. But then when you get to that point, you can't make it any smaller. So that's what they call a pad limited, right? So your chip size is determined by the pad that you have. And you can't just take a pad out or add a pad in, right? Because that's the function of your chip. You need that many I/O, right? So I hope
the
I answer your question.
yeah,
Yeah, it's
right. He went on to ask what are the solutions, right? If you have pad limited design. I think I answered it, but you might want to cover it now.
Okay, so I think we 5 minutes over. So
Okay, right.
If I can add a quick answer to that. So in case of the pad limit, so given a die area, you basically can estimate the maximum number of pads that can fit into that die area. But if in case you have design a chip that need extra I/O, so one of the solution is that you design like dual row. Instead of having one row of pad, you can have a second row, but that will increase the die size of the chip. So that is one of the solutions. And the other solution, of course, that you try to optimize the dimension of the pad. Like you try when you design a pad, you request the I/O designer to have the pad a little bit thinner. I mean the width is smaller, but increase the length a little bit. Again, that's also had an impact on the die area as well, but it's another option.
And the third option would be bulk grid array, where you use the bumps, right, as IOs. So that's another option. And the dual ring is referred to as stagger pads because they're going to be staggered so that they can be bonded out.
Right.
Yeah.
Right. I mean, so when you have option for different packages, that's right. So, but most of the time you are limited to certain package already, right? Certain type of package. So
yeah, I have worked on pad limited design there was nothing. They just deal with low utilization. They type out. So
yeah, usually for a simple design, it's more likely it's going to be pad limited. For the complex design, it's not going to be, right? So yeah.
Well, to our respect to those who have to make it to the next class. Thank you very much. If there are more questions, we can ask in the Google Classroom as well. All right. Thank you everyone for the question. I love them.
Yeah.
Please keep them coming.
All right. Thank you everyone.
The recording has stopped.
I think we're going to end the class right now.